Hey guys, today we are going to continue talking about kind of position in a location. We're going to extend the idea of percentiles to kind of a general distribution that is symmetric and actually continuous. This is really going to be the first time we see what we call a continuous distribution. So, the idea we're going to start with today is the idea of a relative frequency histogram. No, my board's not quite working for me. So we have a relative frequency histogram, and think about what that does. So it takes each class of your histogram and plots the percentage instead of the actual frequency. So what's kind of neat about these relative frequency histograms is that we can actually calculate percentiles using a relative frequency histogram. Here what we have is we have a group for this data right here of 947 seventh grade students and their test on the Iowa test of basic skills or whatever. So if I wanted to find the percentile for a score of 6, all I would have to do is kind of like doing a cumulative relative frequency, which is what we learned about last class, but with a graph. So all we would do is take all these bars over here, and we'd add up all these percents, and that would be all the total percents of the students who scored less than a 6. And that area right here, this area would be a percentile for a score of 6. So, hold on one second. Let me pause this video and fix something. I'll be right back. Okay, sorry. So, what we have here is we have what's called a density curve. And what a density curve is it's going to be a curve that kind of approximates a relative frequency histogram. See if I can do this fancy trick. Close. And it didn't work. Okay, so a density curve is going to be like this curve right here, where it gives an approximation for a distribution. And there's a few things that we know about density curves that happen with every single one. And here are some things about a density curve. A density curve will always lie above the horizontal axis, and this is because it's always going to give you percents, and we'll never have negative percents. And so we have no need for anything below the positive x-axis. Also, since we're looking at a relative frequency histogram, then all of those bars should add up to 100%. So we're going to kind of think of this in terms of decimals. So another property of a density curve is that the area underneath that curve is exactly 1. Now you're going to be asked on a few questions to prove that something is a density curve. So if you want to do that, all you have to do is show that these two statements are true. So to prove, let's say a graph represents, ran out of room. A density curve show these are true. We'll have an example of this in just a few minutes. All right, now the median of a density curve, this is what this says down here, is it's going to be where exactly half of the area falls to the left and falls to the right. The mean is a little harder. And what they say here is that the mean of a density curve is where it would balance if it were made of solid material. So you have to think that the mean would be the point where you're not just considering the number of observations, but also those x values at the bottom and what values they're taking on and how that would make it balance. Generally, the rule for me when I'm looking at a density curve is, just think of the rule that if it's a symmetric distribution, the mean and the median will be in approximately the same place. And for a skewed distribution, the mean is always closer to the tail. That's kind of a better visualization of trying to discern between the mean and the median. So here we have two examples. This shows two different density curves, and then here is the mean and the median for that one. Here is the median for this one, and then obviously the mean is pulled closer to the tail. Now some people want to put the median at the peak, but the median will never be at that peak. It's always going to be a little off. All right, so here I have a few examples for you. I think that this question is pretty self-explanatory. You're just going to kind of read through the question and see, I guess, just answer the questions. Do remember that when you're doing 27, the area underneath the curve represents the proportion or the percent. And this is going to be kind of something that resonates all throughout this lesson and next lesson. The area under the curve, like we talked about with the relative frequency histogram, represents the proportion or the percent. And you would think of this, although it's a straight line, this would be our curve. And you're just going to use this graph to answer the questions. So pause the recording, come back and answer the questions, and then come back and I'll give you the answers. Okay, so here are our two sets of solutions. Let's talk about 31 really quickly, because I think that was pretty simple if you just looked at that example on the other page. On part A, we have a skewed right distribution. So the mean is going to be pulled towards the tail. So I also told you that the peak is never going to be the median because it's not going to have half observations on one side and half on the other in a skewed distribution. You're always going to have more on the tail side. So what we have here is we know that the mean is going to be pulled toward the tail, so that's going to be C, the one farthest to the right, and then the one to the left of that, B, would be our median. Now on part B, although it's not necessarily a what we call a normal distribution, it doesn't have one peak, it is symmetric. So for any symmetric distribution, the mean and the median are always going to be in the center. And so B would be both the mean and the median. All right, so let's talk about this over here. So we want to explain why this satisfies the properties of a density curve. Now, when you're talking about area under the curve, you're talking about this total area right here. So the easiest way to find the area of that is just think of it like a rectangle, length times width. So the total area is going to be 3 times 1/3, which is 1. So it meets that requirement. And it also totally falls above the horizontal axis. So it also meets the other requirement. All right, the next part asks us to find the proportion of accidents that occur in the first mile of the pathway. And that proportion is just, you're just going to look at area again. Remember, the proportion of accidents that occur is just going to be the area between 0 and 1. That's how a density curve is defined. It's just going to be the proportion or the percent of anything is just going to be the area between those two numbers. So if we want to think about area, we're going to think about a rectangle again. So we're going to think about length, which is just going to be the big number minus the little number, 1 minus 0, times the height, which is 1/3. So 1 times 1/3 is just 1/3 or 33%. Part B asks us a similar question, except they want to find the proportion of accidents between the 1 point, no, sorry, I always say the big numbers second. Anyway, between zero point 0.8 and 1.1. So we want to find our width, which would be, or I guess our length, however you want to say it, which is going to be the distance between 1.1 and zero point 0.8. So I'm going to subtract those and then multiply it by the height, and I get 10%. So sometimes you'll see density curves that look like a normal distribution, like a bell curve like this. And then sometimes you'll see them where they look more like this. And make sure that, you think about, okay, does it follow those properties of a density curve? And if it does, then all you have to do is look at the area between the numbers, and it'll show you the proportion or the percent. Okay, so now we have one special density curve that we're going to talk about an awful lot this year, and this is called the normal curve. Okay, the normal curve is a symmetric one-peak graph. It's going to be a bell curve, pretty much. And a normal curve has a lot of similar properties. They share a lot of properties. Uh, it's a special group of density curves, you would say. Because you know the normal distribution is always going to have one single peak and be symmetric, there's a lot of things that you can tell just by giving the mean and the standard deviation. You can completely describe a normal curve just by giving its mean and standard deviation. Obviously, if it's symmetric, they're both going to be in the middle. The bigger the standard deviation, the wider, more spread out of a normal curve you have. And then we'll talk about how to sketch them. A way that we can abbreviate a normal curve, I'm not quite sure why this looks like this. Let's put this here. It's kind of fun looking. And put that there. Is with a mean and a standard deviation. Now notice that we used different letters for mean and standard deviation here. So I want to talk about notation for just a second, and then we're going to talk about this example down here. So these are two Greek letters that we have here for mean and standard deviation. This is called mu, and this is called sigma. And this is just mu is a lowercase Greek m, and sigma is a lowercase Greek s. Now, we have been using x bar and s to represent mean and standard deviation. Why we have different letters here is because mu and sigma represent the mean and standard deviation, for an entire population. So when you're given a density curve, then what happens is it gives us a picture of the entire distribution. And so since we're looking at the entire distribution and not just a sample, we have different letters to represent mean and standard deviation. Let's write this again. This is mu, which represents the population mean. Remember, x bar was what we were using before, and this is our sample mean. And then sigma is our population. I'm going to say pop, STV, dev, population standard deviation, and then S sub x is our sample standard deviation. Now, it's going to be really important to us later to be able to distinguish between what happens in a sample and what happens in the population. Um, and so that's why we have different letters to represent both. What kind of the idea in statistics, what we'll get on next semester, will be taking data from a sample and using it to project something about the entire population. And that's generally what you want to do. You know, you want to do a drug study where you're only collecting 50 pieces of data and be able to tell you what's going to happen to all the people who take the drug. If not, then there's really no use in doing these types of studies because then it would only apply to the 50 people that you're testing it on. So it's going to be really important for us later to distinguish, what came from the sample and then maybe what came from the population or whether we're projecting it into the population. All right, so the easiest way to graph a normal distribution is going to be to sketch the curve. Mark the peak in the middle as the mean and the inflection points as one standard deviation on either side. So let's talk about inflection points for just a minute. I'm actually going to go through this example with you because I didn't give you an example on sketching a graph. So we're going to do number 41 together. Okay, so what happens is I use this word inflection point and I didn't really tell you what it is. So let's first sketch our normal curve. You're going to have to, mine are always kind of lopsided, but that'll be okay. You're going to have to get really used to sketching these normal curves out because anytime we work a problem where we use the normal distribution, we generally have to draw a picture and show kind of what area it is we're finding. So you'll get pretty good at kind of sketching these out fairly quickly on your paper. If you're not good at it now, that's cool. You'll get better at it later. All right, so I told you first that the mean and the median are the same. They're in the center of the distribution. So we're going to mark that first, that peak of our distribution. And we're going to mark the mean or the median. Here they've given us the mean. So I'm going to mark that this right here is 69 inches. Okay, then when we're drawing out a normal distribution, like they've asked us to do, we want to locate at least 2 standard deviations on either side of the mean. Now, I have a 69 here. I don't really know how wide 2.5 is. Standard deviation is 2.5. I could make this 2.5. I can make that 2.5. I mean, I don't have a scale here, but I have lots of different normal curves. Do I have a tall peak? Do I have a flatter peak? And how we figure out where to mark the standard deviation, this is actually a really cool thing, and I think it probably has to do with calculus, but I've never studied the theory behind it. The inflection points of your graph. Inflection points are going to be where a graph changes from concave up. This would be concave up, right? Here. That would be concave up. Oops. That would be concave up. To concave down. So then, let's see if I can use the green. This right here would be concave down. And at these points right here, these are what we call inflection points. So I have one there, and then I'm just going to guess the other one's about right there. I don't think it's very perfect, but it'll be okay. And then these points right here on my curve tell me where one standard deviation is away from the mean. So this curve over here, this black mark that I just made, is going to be the mean, which is 69, plus one standard deviation, which is going to be 2.5, so that's going to be 71.5. And then this over here is going to be my mean minus one standard. Sorry, dropped the microphone. Minus one standard deviation. So that's going to be, let's see, 66.5. Now I have some scale. I know that, although it's not perfect, should have done a better job, that this is approximately 2.5, this distance right here, or this one right here, whichever you want to use. I never expect y'all's drawings to be perfect. Mine are never either. So I'm going to use this as a guide to mark 2 and then 3 standard deviations on either side. And then I'm just going to keep adding 2.5 to the previous value to get my next point. So this right here is 2.5 over, so that's going to be 74. And then this one is 2.5 over, so that's going to be 76.5. And then we do the same thing to the right side. except I'm going to subtract 2.5. So that means this one is going to be 64, and then this one's going to be 61.5. So this is the answer to their question. They say draw a normal curve on which this mean and standard deviation are correctly located. So we drew the curve first. We located the points where the curvature changed, which were these points right here. And then I marked the horizontal axis. You do have a homework question similar to this, so you definitely want to know how to mark those. And I never expect for you to be perfect when you're finding your inflection points, but just do the best job that you can. Okay, so the last thing we have to talk about is we have a really special rule that applies only to the normal distribution. So we have what we call the 68, 95, 99.7 rule, which is a big mouthful. So the 68, 95, 99.7 rule, I don't quite know why all this is scooted over, shows us, oops, let's do this actually. Okay, that works better. Tells us what percent of our data in a normal curve fall within 1, 2, or 3 standard deviations of the mean. So we have this rule. We know this only works for the normal distribution. It doesn't work for any other shape of distribution. But we have this rule that says in a normal distribution, approximately 68% of my data will fall within 1 standard deviation of the mean. Approximately 95, so this right here should be 68% of the total area under that curve, right? Total area is 100%. That blue right there marks 68. All right, so 2 standard deviations away from the mean, 95% of my data falls in a normal distribution. So this red area right here, all of this red area represents 95% of the total area under this curve, right? Total area is 100%. 95% falls within 2 standard deviations of the mean. All right, so the last one is 3 standard deviations, which is almost all of it. It's 99.7%. So that means this total area that I'm shading here in green, all of this total area is 99.7% of the total 100% area underneath the curve. And that's some pretty ugly colors right there. And so what we can do is we can find the percent of observations between certain values using this rule. This is how we're going to apply it. So we have this example down here. The first thing that they ask us to do in part A is to sketch a normal density curve for the distribution. Label the points that are 1, 2, and 3 standard deviations away from the mean. So we're looking at those Iowa test scores again, and we have a mean of 6.84, and we have a standard deviation of 1.55. So let's first draw out this curve, just like we did on the other example. I think I did a better job that time. So here is my mean. So this part in the middle is going to be 6.84. And then I have, let's guess that this right here is 1 standard deviation. And that would be 2, and that would be 3. To get 2 and 3, I'm just guesstimating this distance between the mean and 1 standard deviation. So let's guess that and that over there also. All right, so I'm going to start adding 1.55 to get my 2, 3 standard deviations away from the mean. So if I had 6.84 and 1.55, I get 7. Lord, I can't read that. Okay, hold on one second. Let me pause this and get my calculator. I can't read the numbers out here. Okay, so here I've drawn it out for you. I've labeled the mean, and then I've just subtracted 1.553 times to get the left side, added 1.553 times to get the right-hand side, and I get these values down here that I couldn't read before. Okay, so what we want to do here is we want to look at the different percentages between the values. And so what I want y'all to do, maybe on the back of your notes or something, is I want you to write down this little chart that I've made that I'm going to draw out for you. So sometimes they like to ask you to find random values, not like, it'd be fairly easy to find the area between 5.29 and 8.39, because that's one standard deviation on either side of the mean. So we know that that would be 68% by the rule. But we can also break it up and find areas between other values. So let me show you how that would work. So I'm just going to kind of mark this. This is my mean. Just going to guess that's one standard deviation. This is two standard deviations. And this is three standard deviations. Let's say plus. Over here, this is minus one standard deviation, minus two standard deviations, and minus three standard deviations. Okay, so I know that 68% of my data falls between a negative standard deviation and a positive standard deviation. So now, since my distribution is symmetric, we have a lot of cool things that we can do to figure out kind of the different pieces. So if this total area right here is 68%, right, between these two values, then this right here is 34%, and the other side is also 34%. So if I asked you, what percent of the data falls between 6.84 and 8.39, you should be able to tell me that's 34% of my data, because it's just one between the mean and one standard deviation, so it's half of 68. Okay, so what if I asked you to find the area between these two values, 1 and 2 standard deviations? And so what you could say is, you could say, all right, I know that from here to there, that's 95%. So if I subtract 68 minus 90, or 95 minus 68, I get the area of these two pieces right here. You can see where I'm drawing. Since it's symmetric, these two pieces have the same area. So what you get is, you can divide this in half, and this gives you the area of one piece, which is going to be 13.5%. So both of these little pieces right here have an area of 13.5%. And then you can use that same trick to find the area. Switch colors on you right here, right? So we know that 3 standard deviations is 99.7. So if I take 95, and I just keep doing that backwards. I keep wanting to get negative numbers. If I take 99.7 and I subtract 95, I get the area of these two things in red. And if I divide that in half, this gives me the area of 1, which is 2.35%. If I did that right. I don't know if I did that right. Somehow. No, that's right. I'm crazy. Right? Yeah, 2.35%. Because it's going to be 4.7% divided in half. All right, now the total of your area isn't between 3 standard deviations, only 99.7. So the total area under the curve is 100%. So if we want to find the area of these two little tiny tails over here, this green, you can barely see that one, then all I do is take 99.7 And I subtract it from 100 and I divide it by 2, which gives me 0.015. No, 0.15%. Sorry, getting my decimals wrong. So that green area is 0.15%, and this over here is 0.15%. And you can use this little table that I've given you if they ask you for certain values. Say I asked you for the area between 6.84 and 9.94. My green marker is not working for me. Then all you'd have to do is you'd come down here and you'd say, okay, this is going to be 34% plus 13.5% is equal to, and that would be 47.5%. Now, there are lots of ways you can be intuitive about this. There's lots of ways you can come up with getting these areas, either using this table that I've just given you or using the empirical rule, either or the 68, 95, 99.7 rule. It doesn't matter to me how you want to do it. Let's look at this example and see how they do it. Okay, so what they do here, they want to find the area of the scores that are less than 3.74. So let me go down here and see where 3.74 is. I have it right here. Okay, so one thing I know, this is 2 standard deviations below my mean. So I know that 2 standard deviations is 95%. So if this area right here between these two values is 95%, I could take 100 and subtract 95, and then that would give me the area of my two tails. I could divide that in half, and I would get 2.5%. Another way that I could do this is I could go to this table that I've just made, and they want less than 3.74, so I could just add these two values together, the ones with the arrows, and I would get 0.15 plus 2.35, and which is 2.5. So either way, you come up with the right answer. Now, unfortunately, you wouldn't be given this table that I've made you on a test. So you would have to maybe either make it yourself or be a little ingenious about how you'd come up with finding these answers out. Okay, so that was B. Let's see what C is. What percent of the scores are between 5.29 and 9.94? So 5.29 is 1 standard deviation below the mean, and then 9.94 is 2 standard deviations above the mean. So let's see what I would come up with here. Now, one of the ways I could do this is I could say, okay, I know that 5.29 and 8.34 are going to be 68%. And then I just need to add on, if you can see it, I've marked the mess out of this little piece right here. So I know that between 3.74 and 9.94 is 95%. So if I want this little piece right here in black that I've just drawn, I can do, let's see, 95 minus 68 divided by 2, which is 13.5. So I can do 68 plus 13.5, and I would get, Lord, I can't do math in my head, 81.5%. I thought that's what it was. Now, you could also use the picture down here that I've given you. We're 1 standard deviation below the mean to 2 standard deviations above the mean. So it's going to be 34 plus 34 plus 13.5, and that would give you your answer. Okay, so use this table that I've given you, or use whatever tricks you'd like to answer the example at the bottom of page 5 in your notes. Last page, sorry. I don't know if you also have page numbers on them. And then come back and I will give you the answer. Okay, So take a look at this solution. I've drawn the picture out for you so we can kind of talk through it. Oh, I did this wrong, actually. Let's try this again. So the first thing they asked me is, what percent of men are taller than 74 inches? So taller than 74 inches is actually going to be this area over here. So 74 inches is 2 standard deviations. So I can do 100 minus 95 over 2, which gives me 2.5. Or you could do 2.35 plus 0.15 from the other table and also get 2.5. So the next one, they say, what heights fall in the middle 95%, or what heights do the middle 95% of men fall? And so the middle 95% is going to be 2 standard deviations, so that's 64 to 74. Part C wants to know what percent of men are between 64 and 66.5. You could go read that off the other table, or you could take the 2 standard deviations, which is 95, subtract 1, that gives you the area for these two kind of wings right here. Divide that in half, and you get 13.5. All right, part D says a height of 71.5 inches corresponds to what percentile? So remember, we're looking, this is giving us percents, so it's also giving us percentiles if we do everything to the left of it. So if we look at 71.5, I could go through and add up all of the values right here from your table. But one of the things that I like to remember when I'm doing these types of problems is that 50% is always to the left of the mean and the right of the mean. Because remember, we have a perfectly symmetric distribution, which means the mean and the median are in the same place. So that means that we're going to have 50% to the left of 69 and 50% to the right. So I just took all the way up to 69 and it was 50. And then I knew that right here between 69 and 71.5 was 34. So I get the 84th percentile when I add those two things together. All right, so next class we get to talk about calculating all the possible proportions or percents for a normal curve. And we have this special table that we can use to calculate them. So kind of extending the idea of this empirical rule to all the values possible between, I guess, honestly, negative infinity and positive infinity. Anyway, so do your Unit 1, Day 8 homework. We're on Day 8 now, and it'll be due next class. After we finish Day 9, we'll have 1 day of review, and then you'll take an exam over everything in Unit 1 after that day of review. So start looking back over everything, make sure that you're prepared.